మంజు కింద కొరియర్ వచ్చిందండి ఇప్పుడు పిన్నికి ఫోన్ చేస్తా అంటే ఎత్తట్లే. హలో ಎಲ್ಲಿ ಬರುತ್ತೆ ನಮ್ಮ ಮೊಬೈಲ್ ನಂಬರ್ ಬರುತ್ತಾ? ಓಕೆ 762319 ಹೌದು ಹೌದೌದು ಕೊಟ್ಟಿದ್ದೀರಾ? ಓಕೆ ಥ್ಯಾಂಕ್ ಯು. These 3 days time. Hi everyone, good afternoon. I think we have good majority. We're just waiting for Ashwin.
Darshan said he have something to complete.
Okay, so
He will not be able to join.
Lahiri will be leaving.
Lahiri is leaving now.
And Ashwin.
Ashwin will join.
Okay. Right, I think Kruthika we can get started. Anyway, this is recording, so if someone listens, we will share the link.
Yeah, I will start. Yeah, you are able to see my screen?
Yes.
Yeah. I will start then.
Please.
Okay. Yeah. Yeah, hello. Yeah, Vishwa.
Yeah, Kritika, it's not you. I think Vishwa is, I think.
Okay, Ravi, I will start. Yeah, good evening. Thanks everyone for joining the session. So today I have chosen a topic overview of TVM. So I'm just giving the overall briefing of what this TVM, how it has been started. So I have
Bye,
taken
bro. Message me, okay, bro? When you reach now, message me.
Darshan, can you go on mute? There is a disturbance.
Ilbara.
Hello, Darshan.
Darshan and Ashwin, you both has to go on mute.
yeah.
Yeah,
So I have
please.
taken a reference with respect to the TVM paper, the first paper from the TVM. I've taken that reference. I'm giving you the overview of TVM. So what is this? TVM is tensor virtual machine. Okay, so the goal of this TVM is to deploy deep learning everywhere. So train with a ML framework of your choice, be it the TensorFlow, MXNet or the PyTorch, Keras based models, and leverage any release or version of the chosen framework. Also, you have a leverage, you can choose, means if there is any version change, that also should be considered. And we should be able to deploy to any hardware platform on the edge or in the cloud. So the goal was this. So we should have a end-to-end compiler stack where the deep learning developer have the leverage of training the model or model on any of these frameworks and deploy it on a wide range of hardware backends.
Got it.
Okay, so this was the goal of the TVM. So the slides and most of the complete material is taken from the TVM documentation only. They have a vast, very good documentation.
Okay.
So this is the industry challenge for deployment. This is just to have the context with the present latest with the Xilinx. They also talk with a similar thing. Means whatever may be the framework, it has to be able to deploy in the various hardware. So who actually, okay, to in order to have or in order to achieve this deployment, each operator in the graph, I mean any model can be represented as a computational graph, nothing but a operator and the data flow or the data variables. So each operator in the graph must be optimized for acceleration and hardware target. So each of these operator should be optimized for a particular hardware. So who actually optimizes this graph? Who actually optimizes means for right now, to have a reference with NVIDIA, we have a CUDNN libraries. So we should have some compiler or a library which actually optimizes this graph from the frameworks to a particular hardware. Okay, so but there is no interoperability, means we have a PyTorch model, and if I have to deploy that on a Qualcomm or any of these other edge devices, there should be CUDNN similar to CUDNN library should be written, or it has to be developed for each of the operator. Okay, so comparative, it is a tedious task because we have a day to day, there will be more number of models, and the new operators are also with applications, many kind of models, or that models and the operators are in use in daily basis. So it will be very hard for the hardware or the chip level or the compiler for the system engineer to develop, to support the operators for a particular hardware device. It can be possible, but it takes time compared to the development with respect to the models or the operators. Okay, so yeah, so the abstract is clear. uh, Whatever may be the model, it has the whatever may be the model framework, it has to be deployed in various platform. So how this TVM achieves this? TVM is an end-to-end optimization stack that actually has a graph level optimization and the operator level optimization. So in order to provide performance portability to deep learning workloads across diverse hardware backends. So these are the two optimization steps or the category is graph level optimization and the operator level optimization. So what is not TVM? TVM is an open source Apache project. It's an open source project, an enabler for diverse inference platform, a high performance neural network compiler and runtime. So what is not a TVM? It is not a framework for model training, an intermediate representation. Although why we call this as why we there is a point of intermediate representation, because that Onyx and TensorRT, there is a comparison, but I will not go with the Onyx comparison now. So I will go much more deeper with explaining the TVM part. So the number and diversity of accelerators pose a adoption, same thing, whatever I gave the reference. So why it is difficult for the frameworks to deploy with the various hardware? Because there is a main criteria is the memory organization. So we have CPU, GPU, TPU. Last week, Darshan was explaining with respect to the GPU, the scheduling and the sharing of data. So there is a diverse architecture with respect to the hardwares. So that is the major challenge. Okay, so this is the TVM inference framework stack. So there are various level. So I'll try to go just a briefing of each of the steps. So this is the present architecture or the framework for the TVM. Okay, fine. Okay, so as I told, even the TensorFlow or the PyTorch supports this optimization with respect to graph level. What is this optimization? Graph level optimization means auto differentiation, dynamic memory management. So many maybe you may be knowing what is the definitions of this or the meaning of auto differentiation and all. That's what are the optimization steps? It is a we should take it as a separate. What are the available graph level optimization or the computation tensor level optimizations and all? So today I'm just making you familiar with the terms with respect to the optimizations. So auto differentiation, dynamic memory management. I'll in the next I will just compare with the TensorFlow also. So the graph level optimization are often too high level to handle hardware backend specific operator transformation. So current operator level libraries that DL frameworks rely on too rigid or too specialized to be easily ported across the hardware devices. I mean to say TensorFlow also supports this graph level optimization, say for using this grappler. But across the hardware, it is not feasible with the Xilinx or the other edge devices. Across for each of the hardware, it is not feasible. So there should be a common platform where the TVM talks about whatever will be the platform or the either hardware or the uh, models. They should not. It should be there should not be any dependency with a third party. So you just use the TVM and you should be able to run you should be able to deploy any model on the particular hardware. So to address these weakness, we need a compiler framework. So optimization approach is across both graph level and operator level. Okay. So I just made a comparison. So grappling is with respect to the TensorFlow. It also provides you the operator level and the graph level optimization with respect to the GPU, TPU, and the mobile. So this is the latest thing. Okay, so I was talking about, let's go some more detailing about the TVM only. Okay, so TVM presents two-level optimization. A computation graph optimization layer, high-level data flow rewriting. So in that, we have a method called high-level data flow rewriting as a tensor optimization layer with schedule primitives to address. So there are two computational graph level and the tensor optimization layer. So what actually inside this tensor optimization layer is memory reuse across the threads, tensorized compute intrinsic, latency hiding. So I'll try to cover each of these optimization techniques. These are the various optimization techniques with respect to CPU, GPU, or the TPU. or with deep learning accelerators also. Also, apart from this, there are different methods also available, but in general, these are the possible optimizations required with for all these hardwares. So coming to the system overview, uh, just to have a usage of this TVM, I have taken this part. So TVM by using an example to walk through its components. So we have any existing framework, the model will be trained and we have a model ready and transform it to the computational graph representation. So most of these frameworks provide this. So we have a computational graph representation of the model. Then this has to be rewritten to the data flow, high level data flow rewriting to generate an optimized graph. So we will be applying some constant optimizers. There are different optimization techniques, constant folding, and various optimization techniques. So that's what most of these are embedded with the frameworks only now, but still this TVM also talks about how to write or how to optimize this computational graph. So the operator level optimization model must generate efficient code for each fused operators in the graph. So operators are specified in declarative tensor expression language. Execution details are unspecified. So they actually use the tensor expression language, a kind of a programming language similar to based on the tensor called a relay intermediate representation. They relay intermediate representation. Using this programming language, they have defined the data structures, looping structures, functions uh, on these data structures. So we should be able to express or write our computational graph with respect to the model in these forms, or using this tensor expression language, we have to write the high level data flow format. So TVM identifies a collection of possible code optimization for a given hardware targets. So as I told, for a given hardware target, there are some optimization methods available, like in memory reuse across threads. To achieve memory reuse across threads, there are some optimization methods. Tensorized compute intrinsic latency hiding. So these are the three possible or optimization requirement with respect to various hardware. In order to achieve this, there are different methods. So the TVM identifies a collection. So TVM has to consider all the possible optimization techniques with respect to different hardwares. Okay, so and scheduling, it has an auto scheduling of each of these optimization techniques. Okay, so yes sir, to start.
Kruthika, go to backslide.
Yeah.
No, not this. The next one. Okay. All right.
Go back.
One slide before this. One slide before this. Yeah.
Overview.
Okay. Now here, when we are talking about the TVM ability to schedule the optimization based on the hardware,
Yeah.
right? How does it know the hardware, each hardware specialty, so that it actually has the optimization schedule? So it doesn't have a probing mechanism, or one has to manually enter it, or how is that?
Actually, that's what each of say Xilinx has some hardware details. Each,
Right.
yeah, for TVM has included each of these kind of hardwares using,
Okay.
and it has generated the code with using the tensor expression language. Using the relay, they have generated the code. That's what, see, with respect to memory optimization, there can be five methods. All
I
the
get
five.
that. So
Huh,
I have a question here. Allow me to complete.
yeah.
So now let us say Xilinx is a popular board. They might have included it. Okay. Now
Okay.
let us say I am creating SAN logic hardware. Okay.
Okay.
So for the SAN logic hardware, for TVM to create an optimizer for SAN logic hardware, is there any steps that they have prescribed, or it has the mechanism to understand the device capability by interacting with it, or I as a SAN hardware creator should give the details to TVM. What is that?
All the ways are possible. Either there is an auto TVM. They call it as a auto TVM. It is able to identify the hardware structure. That also possible. Or
Excellent.
we wish to include the TVM as a compiler stack for the various frameworks. We are allowed to use code the TVM according to based on our hardware.
Understood. Okay.
That's what. So either of the things are possible.
Okay. Good.
Be it we are creating a TensorFlow like library, we can leverage this. We can write the various components accordingly. Whatever the step I shown with respect to tensor optimizer compiler. Some things
Understood.
are general. Some things are specific to the particular hardware.
Understood. Got it.
So when you say auto TVM, right?
Yeah.
It will do for the ones which he already knows. For which he does not has seen at all. Will it do it?
Yeah, actually for auto TVM, I have one slide. At the end, I'll come to
Okay.
which is,
Okay, fine. Let's wait for that. Yep.
yeah. Okay, so I was here. So this is the basic or the starting architecture, because they have modified it now. Modified means they have improvised each of the section, that's all. So in general, I hope everyone has got some understanding. There is a framework. So computational graph representation will be given from the framework. And this TVM has a tensor expression language or relay kind of language, where it will transfer that to an optimized computational graph. Some frameworks support this. Even then, TVM has this option, has a support to transfer this computational graph to optimized computational graph using a relay kind of programming language. Then there are some optimization level with respect to also. All those are taken care inside each of this section. And there are some data structures which can communicate with either of the levels. Okay, so basically from computational graph to optimized low level loop program, there is a programming language which actually implements each of these functions. Okay, fine. So end user, as a end user, if I were to use the TVM, this is a simple we just have to import the model uh, and import the model target with the CUDA. It is with respect to the GPU, and you can deploy that with the target. Since it is just a straightforward, I will not go in much more detail because we are more interested with the architecture of it. So we just can import the model. Here the model has been imported, the Keras model, and compiled. All here the graph level optimization is done. Then runtime. Runtime module means we just have to deploy that on a particular GPU. All the optimized uh, techniques are included here. Okay, this is how the model has been defined with respect to the or using the relay. So TVM supports multiple languages, C++, Java, and the Python. So 4 fundamental challenges to the computational graph level and the tensor operator level. So we should be here. I'm just giving you some understanding about what are these computational graph level or the tensor operator level optimizations. What are the challenges? So high level data flow rewriting. So as I told, computational graph is nothing but the node and the edges. Node are represented as the operator. With respect to convolution, uh, addition, multiplication, or the dot product also we can consider as an operator. So different hardware devices may have vastly different memory hierarchies. Enabling strategies to fuse operators and optimize data layouts are crucial for optimizing memory access. So what are the challenges with respect to each of the steps? Memory reuse across threads. As you know, what are the requirement for the GPUs? Similarly, for the TPUs or the DLA, there are some challenges. Means each of these hardware assess the or handle the memory in a different ways. So that is one challenge. So tensorized computer intrinsic. That is the DLA. It also includes the DLA. So as I told, These are specialized hardware which actually implements the our generic matrix multiplication with respect to the deep learning operations. The next one is the latency hiding. Okay, so it's traditional architecture with simultaneous multi-threading and automatically managed cache implicitly. That's what I just want to give overall view. So I'm not going in depth of each of these terminologies. Okay, so optimizing computational graphs. Operator fusion is one method to optimize these computational graphs. What is operator fusion is? Okay, optimization that can greatly reduce execution time, particularly in GPUs and specialized accelerators. This is the purpose of operator fusion. So combine multiple operators together into a single kernel without saving the intermediate result back into the global memory. So operator fusion. This is how our computational graph looks. Okay, for a typical convolution 2D. So operator fusion is combining the two operators. So this is one optimization method. So this actually helps with the memory usage or memory operations. Okay. So these are data layout transformation, transforming the data layout or computational from the computational graph to one form. So this all these methods are achieved with respect with in Onyx or other frameworks also. Other even PyTorch has the support, but in TVM this is how it has been handled. For graph operators, even what are the different steps to optimize these graph operators? There can be four methods: injective, reduction, complex or fusible, opaque. Okay.
Okay.
So the data layout transformation. So again, I have taken only one example of data layout transformation. So tensor operations are the basic operators of computational graphs. They can have divergent layout requirement across different operations. Optimizing data layout starts with specifying the preferred data layout of each operator given the constraint, dictating their implementation hardware. So this is how we have a tensor organization. It's like dividing or matrix tiling. All these are various techniques for giving this tensor data to a particular memory of a hardware. Okay, so we get all these are as a generalized. This is not a new thing, but they are actually this data layer transformation and all they have referred with a halide, which has been implemented around 2013 only. This TVM have completely uses the halide based. Halide is a programming language written in C++, where they actually for basically for high dimensional data like images, handling
What is the language you said?
HALIDE, halide. This TVM completely uses this halide techniques only, which has been implemented in 2013 actually.
Kruthika, somehow your voice goes very low and then suddenly comes high and then goes low. Actually, I think your
Sometimes
mouth,
some half a
mouth,
minute it is going off also.
Off
huh?
also.
Sometimes 15 to 20 seconds half it is going.
Have connected to the LAN also.
No, it's not the LAN issue. Your mouthpiece, your headphone mouthpiece.
Yeah, mouthpiece.
Mouthpiece
I'm
not
holding.
moving.
So you're holding the headphones and stuff.
Yeah, I'm holding it near also.
Maybe whenever you turn sides, maybe that may be the case.
Okay.
Anyway, friend.
Yeah, no, I will try to. I'm louder only. Yeah, okay. So this halide language, they have actually.
Kruthika, we lost you.
Yeah, hello.
Hello, yeah.
Yeah. So that this halide language actually deals with high dimensional data with respect to images. So this TVM completely based on that. So why I told, because the complete reference is with respect to a particular framework already which has been existing, but not commonly used across with respect to deep learning. So this optimizing tensor operation. Next, the data layout transformation, and the next part is the optimizing tensor operation. So tensor expression language, TVM introduces a data flow tensor expression language to support automatic code generation. So unlike high level computation graphs, most of these tensor expression optimization are with respect to the hardwares. TVM explicitly introduces a commutative reduction operator to easily schedule commutative reductions across multiple threads. Okay, so yeah, this is how I'm just showing how the coding with respect to tensor expression language or the relay. And based on this, most of these operators are embedded in a single instruction. Okay, using the lambda, it has been embedded in a single instruction. And this tensor expression methods are used to schedule this particular single instruction. This is how the optimization in one way of achieving the optimization. Just a matrix multiplication. I'm just showing the representation with respect to this language. This actually nothing but a matrix transpose of a matrix multiplication. Only it is computing that, but the way it is it is represented or stored in the memory is in the form of a symbolic. The way it is handled with respect to the memory is different. Okay, the schedule space. Okay, that's what. See, from here, there is a complete different paper where he talks about the schedule tensor expression language and the schedule space. I'm just giving you briefing with respect to this flow. So we have this optimized computational graph, which is similar to the our regular or just looping instruction. This is same. Then loop tiling. Loop tiling means I can say this is a like transforming high level language to an assembly level language, taking care of optimizations. So again, here there are various steps with the scheduling, each of their operator. That's what all these should be taken as a separate section, because each one has a various methods, and the each one talks about each operator, how the scheduling or loop respiration, cache location, parallel cooperation, how each of these operator are handled as a multiple threads. So all these are with respect to that only. Basically, optimizing tensor operation has 3 steps. Tensor expression language. This is how the tensor expression language has been defined. The next is schedule the space. Schedule the space means how to give these instruction to the memory. That is the next step. For that, there are various methods. The next one, last one, is nested parallelism with cooperation. How each of these threads or each of these processing, each of these threads are handled with respect to GPU or with respect to TPU. Okay. Yeah, comparatively, it's a complex thing. We have to take each of the step, each of the processing as a separate. So today I'm just giving you the complete overview. Few of the things I have documented, or I have been with a extra understanding also. But comparatively, it is various domain expertise is required, I think. Okay. So yeah, that's what for latency hiding also. Compiler support for latency hiding. How I'm just making a point. Each of this optimization with respect to memory across the various hardware is taken care with the TVM. So even the main thing is the latency hiding. Latency hiding, most of the GPUs will take care, but the TPUs explicitly this latency hiding has to be coded, or it has to be taken care. So that's the input I have here. Yeah, that's virtual threading. That's what I told. TVM actually provides this virtual threading schedule primitive for a particular hardware. So combining all the, because each of CPU, GPU, and the TPU addresses this latency hiding in a different way. So in order to solve that issue, TVM provides a virtual threading schedule primitive. So it has a method to handle all the hardware with respect to the latency hiding. So Jesu was pointing out, this is also very important, automatic kernel optimization for deep learning on all hardware platforms. So they say that there is an automatic kernel optimization for deep learning. Means we start from the particular framework, and we using the TVM we have achieved the optimization, and we have deployed that on a hardware. So there is a tuning, there is a ML based auto TVM. Means some parameters can be tuned. Means this deployment or the inference can be optimized. Okay, this is what you meant, Jesu.
Yeah, yeah, I
Yeah.
think so. I got the point. So they have some RPC runtime, which
Yeah.
is always connected. Yeah,
Yes.
yeah. I
So
think they will get to know whatever they did in the compilation optimization. They will check it on the hardware,
yeah.
and based on how it performs, they will know exactly what worked and what did not work, and come back to tune it. Good.
Yeah,
This is
and for
interesting.
this tuning also, they have made it as automated. And automated, I mean to say, there is an ML algorithm for this.
Okay.
There is an ML algorithm for this, which actually achieves. So they call it as an auto TVM.
Right, they have created a ML algorithm for this. Is it?
Yeah.
Yeah,
Wow.
because
Uh,
they will get all the data, no, Kamal? They can
Yeah.
get the data, right? The timing data, these data, what are all those things, right? How much memory one particular optimizer step used. Those are the
Yeah,
things they will look for. Yeah.
beautifully done. Beautifully done.
Yep.
yeah, and they have made a comparison with respect to the performance of auto TVM also.
Mm-hmm.
I'm not going with, because comparatively, whatever the implementation they have done, it is a 3x faster with the already available things.
Okay.
So I'm not going with the comparison. Yes, with auto TVM, there is a 3x faster inference is achieved already with respect to various yes devices or the platforms.
Okay.
Wow, 3x is it?
Yeah. This most of the references are taken from the 2017, the first paper. I have tried to include the present. This is from the already the 2018, I think. This is with respect to the present. Present means there is an addition of VTA. I was telling, no, uh, this VTA part again. That is a different thing, but this is the present diagram I have taken. Next one is code generation and runtime support. This what I am talking about, the deployment RPC part. So for a specific tuple of data flow declaration, so okay, TVM can generate lower code by iteratively transferring the schedule tree, inferring the dependent bounds of the input tensor, generating the loop nest in the low level code. The code is lower to the in-memory representation of a imperative C-style loop program, reuses a variant of halides the loop program's data structure in this process. It actually uses this halide support in order to transform the code to a particular hardware dependent or a C style of programming. Again, passes from halide for common layering primitives like storage flattening, GPU acceleration, synchronization point detection, virtual thread injection, model generation. So whatever I explained, all these are various steps are completely taken care with the code generation. Inside each of the points actually uses the various optimization techniques. So in general, this is the steps. The loop program is transformed into LLVM or CUDA Metal or OpenCL source code. So using various optimization techniques and the support of the frameworks and the compilers, compiler techniques. Finally, compiler uh, supported source code will be ready. Then the runtime support. So TVM includes infrastructure to make profiling and auto tuning easier on embedded devices. Targeting on embedded devices for tuning requirement. So cross compiling on the host side. These are the just steps with respect to how this can be deployed with the particular embedded devices. So they actually targeted from the embedded device point of view or FPGAs, also with the FPGAs. So all these points are uh, uh, put up in the first paper. Yeah, compiles the program on the host compiler. It uploads to remote embedded devices. It runs the function remotely, and it assesses the result in the same script on the host. So this auto TVM picture actually explains the whole of the thing. So this is how, as I told, with respect to embedded device, these are the steps. Upload the model to remote, get the remote function. Yes, there is a two-way communication. Copy the data to remote, get remote array handle. Run function on a remote, get the profile statistics back. Copy data back to host for correctness verification. So whatever the code you are seeing, this is the relay code. Okay. So since the latest was with respect to the Xilinx, I have included this diagram with respect to Xilinx. The Xilinx has a DPU support, DPU library or the compiler support for running various frameworks. But along with the TVM, it is able to achieve the faster inference or deploying with respect to the various models. Again, so why I have made a point with the Xilinx, because the way the TVM is embedded inside that Xilinx environment is customized. Customized means already there is a DPU. So now Xilinx is trying to support the hardware with respect to the DPU along with the TVM or TVM only. We have both option. Just using the TVM, it is able to we are able to deploy the models, or along with the DPU and the TVM also we are able to run the DL models on the Xilinx devices. So I'm just with respect to the present context, I have made a benefits and the limitations of a TVM. So TVM can run any layer and it passes from a model on x86 or ARM CPUs. All computation and related operators from CNNs to LSTMs, BERT, in any NLP RNNs. There are limitations. Example, layer of type reads a binary file on disk is not supported. So this was with respect to the FPGAs, but it can be overcome with the VTA. TVM parsers are continuously updated for the latest version of PyTorch, TF, and other frameworks. So PyTorch has along with the PyTorch library only, we have an inbuilt TVM support now. ARM contributes to improving TVM's ARM support. The ML accelerator community is backing projects like TVM and Onyx. So yes, uh, what TVM is doing parallelly is some of the things can be achieved with the Onyx also. So TVM solves industry challenges, continuous improvement through the work of the open source community. So so this is the conclusion. So today I just try to give just an overview of a TVM, but it's difficult to go in depth. So I just made an attempt to give you the just a introduction of a TVM. So each of the topic has to be explored and understood in depth. then only we can get the more holding of the framework or the library. So TVM provides an end-to-end stack to solve fundamental optimization challenges across the diverse set of hardware backends. So I just wanted to convey these 2 points with today's talk. So hope I have able to give you the just at least these two inputs, how TVM is able to achieve these 2 points. Yeah, thank you. The most of the references are taken from the TVM documentation only, and along with the Xilinx. Yeah, any doubts?
One question, do you know what TVM stands for?
Tensor virtual machine.
Okay. And this is registered trademark of Apache. Right? There is Apache only. Okay. Okay, fine. Thanks a lot. Does anyone have any other questions?
Now I have one thing. So whatever we are doing with the Xilinx, right,
Yeah,
Kruthika?
yeah.
Are you planning to do anything with TVM, or is there any POC that you are planning to do? It is
So
Ultranet 96 board.
yeah, if you use the TVM, it is easy. Actually,
I
we
I
the
think it should be inbuilt, right? I don't think there is anything we can do because Xilinx would have already used the TVM. If you see the diagram which you showed, that compiler which is creating the CPU layers and the FPGA layers is already optimized using TVM for Xilinx hardware.
Actually, that's what I told. I made a difference. Differences. There is a DPU support, which
Yes.
actually does the similar things with respect to TVM. But to have in general
Yes.
frameworks, we should go with the TVM.
Yeah. So
No,
what I'm saying is the compilers which you have put in the compiler and the quantizers, right? Which you have put there, right?
Yeah.
So one arrow goes to the Xilinx tensor graph and the graph optimization.
Yeah.
The other goes and it generates, I don't know what is that compiler. Maybe it generates its own compiler for
no,
the,
That is the DPU.
it generates its code, and then it has to generates the runtime code.
no, the runtime code will come always after the compiler. Compiler is not your runtime code. Runtime
No,
code always
no, no,
comes after the compiler, right?
no. Sometimes compilers are used to emit runtime code.
That is what I'm saying, Kamal. It is only after the compiler we will get the runtime code, right?
No, right? Dynamic. There is something called as dynamic runtime language.
That is nothing but interpreters, right? They will do it on the fly.
Interpreter is little different again. Dynamic runtime language actually emits the runtime language based on the context. It is comparable to jitter, but it is not exactly jitter also. Okay, it's just like a jitter, but it's not exactly like jitter also. So DLR has a different purpose. So generally, what happens is if you have a runtime parameters which you are unable, which you are not sure, which you can't forecast at this point of time, that happens only during at that particular instruction that is about to execute. So what it does is it actually creates the code and emits the code, and then again that is given to the runtime. So it is like your runtime and code is emitted in the runtime, and for that you need a compiler. It is like a river. Generally, what we do, we write the source code and use the compiler to compile it. In this case, what happens is that the compiler is used to emit the runtime code, so that runtime directly consumes it. So
See,
it's
Kamal, in both your case, whether it was just a code, you use the compiler, it will emit the runtime code, which is fixed. In the other
yes,
case,
yes,
there are some dynamic parameters which needs to be taken care. In
that's right.
that case also, the compiler will take it. It will emit the runtime code, which will execute with the fixed part of the runtime.
Yes.
Yeah. So
That's what I'm trying to
runtime
say.
is always emitted by the compiler.
That's right. That's what I
Yeah.
was trying to say. These
Yeah.
are the
So
DLL is limited.
what I'm trying to understand is there something we need to do for the Xilinx, or is the TVM already integrated into their framework?
That's exact my point was coming. allow me to continue my question. If there is something which is already inbuilt in Xilinx, I am still fine. But I want Kruthika to take some hardware and then do a POC using TM.
Yeah. So what I'm going to tell her is the next part of her presentation or the knowledge sharing should be to take one Xilinx, okay, and maybe I will give her some details about deep vision, okay, and ask her how deep vision would have used TVM.
Yes.
You
No, that is one thing. That is with respect
see,
to the
because see, I'll tell you where we are going today, tomorrow, or someday in future. We are going to create our own hardware, right?
right.
When we are going to create our own hardware, I need to give somebody, if someone wants to use that, I need to give him, boss, take my SDK. There is an inbuilt compiler for you which quantizes, optimizes everything for you.
Exactly.
Okay. Now you take this, take my hardware and run anything on it. That is what exactly Deep Vision is also talking about. So
Exactly.
what I want to understand is, if I am going to create my own hardware, how will TVM help me? Is it going to create a compiler which knows my hardware nuts and bolts so that it can optimize and quantize very efficiently?
Exactly. That is what it is all about. So apart from next session of Kruthika, what I want is, I mean, we need to take one hardware which doesn't have implemented or doesn't have inbuilt things, and then we build it. We do a POC on it.
Yeah.
You
Yeah,
got
I
it?
will. Yeah, I got it. Yeah, I got
Okay.
it. I will first. That's what I took with the Xilinx because we are in the same context. So I wanted to put this one.
Yeah. So first thing I want you to tell us is the Xilinx framework, whatever we are using, Vivado or whatever, right? Whatever
Okay.
these guys are using,
Yeah.
does it have TVM? First thing,
Okay.
inbuilt. That means whether there is an option for me to enable disable. That means I would like to enable first and disable it so that I can see the difference. Number one.
Okay. Okay.
Number two is, is that possible? If it is not possible, then everything is fine. We will still take any of our models, try to run it on the Xilinx FPGA boards and see what is the performance. So that will also give us a good deal of confidence in terms of trying to understand TVM and how it is already integrated. If not, then what we need to do.
Okay.
Yeah, this is
Yeah.
clear.
Yeah.
The
Clear.
second part of the thing is, which I think there is time for it. I'm going through that DVM, Deep Vision SDK, right? Where these guys have created another hardware. Okay, they have created their own hardware and they are giving us an SDK. They've given an SDK which has an complete simulator. That's what they talk about. I still haven't got my hands too dirty with it. But what they're talking about is their simulator can simulate your model as if it was running on the hardware.
Okay.
Yeah. Okay. So
Yeah.
keeping that in mind, Krutika,
Ah.
how will TVM help? Let's say now take the deep vision out of the story and say put SandLogic there. So
Okay.
if SandLogic is going to create our own hardware, how will TVM help us to first create our compilers, optimizers, quantizers, whatever, right? For the hardware which I am building.
Okay.
Yeah. Okay. These are the
Yeah.
two things. I was just keep it in mind. The second part can come much later, but the
Okay.
first one we can try to see that Xilinx and TVM, whether it's integrated or not. If not, how we get the TVM into picture and speed up the things on
Yeah.
our FPGA.
Maybe that's where the VTA comes in.
Hmm.
Now I understood your query. I will just to try to map whether the VTA is for that.
Okay. Okay.
Okay.
Okay.
As for my understanding, whatever the point you are saying, there the VTA comes in. You
Hmm.
meant there is no hard. There is an uh, so SDK kind of thing.
Hmm.
So whether I am able to use the TVM or able to run the hardware on that using TVM,
Hmm.
that's where the VTA talks about.
Okay.
But still, exact to that, I will map. I will try to map it.
Sure. Sure. Okay. 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 Thanks. First of all, thanks very much for the informative session.
Thank you.
It was very specific to me because there is a project which we are doing which we say code once and run everywhere, right? Core, we call it core.
Yeah.
Code once and run everywhere. So this has been a topic I think I've been discussing with this TVM, I think almost 2 years back. At that time, I know it was not a part of Apache. Okay.
Yeah.
I think, correct me if I'm wrong, Kamal, because when we first saw the TVM website, it was a very bland website, but now the website has become very good. Okay, so
No, it was always Apache. Just, right?
it was all Apache. Okay, so I think they
No,
are
it is
getting.
from Allen School of Washington.
Hmm.
Then after for 1 year, it has been a part of Apache.
Okay. Okay. So anyway, so whatever is that, see, because we have been talking about this and this is our end goal. See,
Yeah.
if this guy can do it,
Actually, so
then we
finally,
can always have our hardware. We can always take any model and run it on any hardware.
Yeah.
Yeah.
Yeah. I also remember I have a text also. Darshan and we have the
Yes.
text. Yeah.
Yes.
Whatever you have
Yes.
explained earlier.
Yeah. Yeah.
Okay. Thank you.
actually, thanks, Kruthika. You have kickstarted this journey of cold ones run everywhere. I'm excited actually. This is something you have been trying to push to Jesu, like
No, 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 no. So for you, you will think that I am not doing, but
No,
everything I
no,
am
I'm not
doing with
saying.
Darshan,
I'm
everything I
not.
am going with Darshan and Tirumol, and this thing is moving towards that goal.
No,
It
no,
may,
I'm
yeah,
no,
yeah,
I'm not saying that you are not
yeah.
doing it this way.
Hmm.
I'm just telling you how we pursued this TVM for last 2 years is what I'm saying.
Yeah, 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 yeah.
Okay, great. Thanks, Kruthika. Thank you.
Thank you. Thanks a lot, Kruthika. Thank you very
Thank
much.
you.
Yeah.
Thank you,
Thank you.
everyone.
Yeah, yeah.
Yeah.
Finally, my dream is happening.